But yeah, basically, it's going to be like what I talked about in the two lectures is basically kind of the known stuff that has been known for at least qualitatively a while now, and all of this is going to be basically new stuff and what's going on at the moment, and perhaps some more of the background of why this is interesting to look at and why people care about it. Okay, so the basic question that I'll be addressing is the following. So how can we probe fundamental physics using astrophysical compact objects? Specifically I'm talking about black holes in this case, because of black hole superradiance. And then fundamental physics here I have in mind these kind of bosonic particles that like a spin zero particle or some kind of axion that you may have heard of. Spin 1 could be a dark photon or some massive spin 1 field. And I'll also say a few things about spin 2 fields and why this doesn't really apply to spin 2 fields the way I have been presenting it. Okay, so in the context of astrophysics, typically the couplings that people consider to actually access these particles and make some observations are basically the axion-photon coupling in the case of the axion, and the kinetic mixing in the case of the spin 1 dark photon. And the reason people consider these, they also consider other couplings, but these are kind of the predominant ones, is that it's the channel through which you can convert something you can't see, which is like the axion, the dark photon, into the standard model photon, which you can observe with telescopes and radio observations, etc., etc. So most of astrophysics is observing photons in some shape or form, and so if you can convert something that you can't see into photons, then you can place constraints or say something about, okay, we should have seen something. And so in particle physics language, this usually comes in these kind of two-dimensional plots shown here. So here this is specifically for the dark photon, which I will get into in just a couple of slides, but the kind of general picture holds true for other particles too, like the axion. So basically on the y-axis you have some coupling to the standard model. So in this case it's kinetic mixing between the dark photon and the standard model photon, so just some coupling through which you convert dark photons to standard model photons. And on the x-axis you have the mass of the dark photon. And then usually all of these colors kind of correspond to different experiments or different observations that have been done to rule out the corresponding areas of parameter space. Okay, so all of these kind of colored regions have some name which correspond to some experiment or some observation that has been done in the past and that can confidently rule out these regions of the parameter space. And the general story is that at the top of the plot there's a bunch going on, meaning there's lots of colors that we have been filling in, and we are very confident that we can rule out particles with such strong couplings to the standard model. And as you come down in the plot, the weaker coupling also means that we have less access to experiments that can actually access these kinds of regions of the parameter space. And at the very bottom is all just white, with the one exception of this band here, labeled dark hole superradiance, which is unique in the following two ways. It's unique in the sense that it only requires gravitational interactions. So basically, even at zero kinetic mixing, you should still expect some observable signature, which is unique because it's kind of the minimal assumptions you need to make for a particle to exist. And then you don't need to assume it's dark matter, which again is a pretty big assumption because you just assume, okay, the Lagrangian describing all the particles that are in the universe. If this Lagrangian contains this particle, then this will happen. This particle does not have to be a fractional or some sizable fraction of the dark matter. Okay, so in that sense, it's a very powerful probe of all these particles because we don't need to assume some coverage to the standard model, and we don't need to assume that it is a fraction of the dark matter. And basically to actually put some constraints on this plot, we need to understand two things. Number one, we need to understand the theory. You have to map some observations to some constraints. We also have to understand the effect that we're looking for very accurately, which means understanding the theory. And then secondly, we need to understand, okay, how can we actually search for these things and place confident constraints. Okay, so the talk is kind of split into two halves. So in the first half, I'll be talking about theory, basically what I haven't covered in the two lectures. And in the second half, I'll be talking about search strategies and how we can actually place constraints on this plot. Okay, so theory. So yeah, this is the one slide recap of the 3 hours of lectures. Basically, you start with a rotating black hole, and this undergoes a super instability at some instability phase. You build up this cloud around the black hole. The black hole has some lower mass and lower angular momentum, and deposited that energy in the cloud. And then over some longer time scales, the cloud dissipates all its energy into gravitational waves, kind of shown in the third column here. And then eventually, okay, you're just left with like very small amount of energy in the cloud, or basically no cloud at all. Okay. So that's kind of super radiance in a nutshell. If we just assume gravitational cloud. And to give you some numbers, so during the lectures I wrote down the numbers for the scalar fields. Now these are the numbers for the vector field, and the vector field numbers are typically orders of magnitude larger. So just as a reminder, we're talking about ultralight fields. So for a 10 solar mass black hole, we're talking roughly about a particle of 10 to the minus 12 electronvolts. And for the spin 1 particles, the instability time scales are even faster. So here order minutes for 10 solar mass black hole, which is pretty fast. I should say that this is kind of the fastest growth rate that you can have, but still it's pretty quick. Gravitational wave timescales, the timescale over which the cloud decays, is order months. And then a frequency, yeah, it's kind of order 100 hertz or so for solar mass black holes. Okay, and so the ways to observe the presence of these clouds around black holes, and therefore infer the existence or non-existence of these particles, is through black hole spin measurements. The black hole spins down, and so if you can find some population of black holes, let's say, that has some spuriously low spins, then you might be able to infer, okay, this process has to have happened for all these black holes to have such low spin. Or just directly by the gravitational wave observations that you can do because the cloud emits gravitational waves. Okay, but before going to these observational signatures, we need to first understand the theory precisely, because here is this kind of a vanilla model, so we're just assuming gravitational interactions. But nothing prevents us from introducing couplings that are quote-unquote natural to the standard model that might be present. Actually, before we go there, So I should say that, as I said, all of this has kind of been worked out and is somewhat known, and particularly the waveform that you produce in this phase here where you emit gravitational waves. The relevant waveform model has been done in the last decade or so by a number of authors that I can't all list here. That involves computing a bunch of things from like growth rates, emission power, frequency evolution, doing all this across the parameter space, so with scalars and vectors, and then it requires some numerical techniques as well as some analytic techniques. Okay, and basically what we did some time ago is to combine all of this in a waveform model. So all of these results are all kind of packaged into like a single source, and the waveform model is called SuperRad. We designed it to be easy to use, so it's written in Python, and you can basically just download it with like a one-liner in terminal. And what SuperRad, as well as the V2 version of SuperRad that we published last year, what it will give you is basically all of these numbers. It will give you the growth rates for all of these given some mass and some spin for the black hole. It will give you growth rates, Howell's frequencies, and so on. To do actual gravitational wave searches, you need these waveform models, and you need them to be sufficiently accurate. Okay, this is just kind of a plug, so you basically can just download it very easily on a laptop and play around. There's some documentation, so it's not just a piece of code that you can't understand without actually having coded it up yourself. If you have questions about the code, you can just shoot me. Okay, so this, we might conclude from this, okay, the theory is well understood, so what's actually left to do for the theorists? And to that, you can answer, we kind of understand the theory, but also not really. And so the reason we don't, I might say not really, are things like self-interactions. So, the axion, at least the QCD axion, is well motivated through like this one CD problem, and the QCD axion has some self-interactions, and we know this kind of by construction. And so we know that it's not just the linear axion model that produces super radiance, but there are some linear interactions that kick in. And in fact, people have shown that if you include these self-interactions, then the cloud may saturate through scalar radiation as opposed to through the spin element of the black hole. Okay? So then you might say, okay, we see black holes with very, very large spins, and so therefore supernovae cannot have happened because it hasn't spun out the black hole. But this is actually not true, because if the self-interactions are sufficiently strong, then supernovae may still have happened, these particles may still exist, but the black hole may not have spun out. Okay? So you need to understand these well-motivated interactions to actually place confidence constraints on, by making these astrophysical observations. Okay, so basically the question is, okay, how do these additional couplings to the Sanan model affect the supernovae story, basically? And so here I'm going to focus on basically two different ways, and they're kind of representative of what might happen in more complicated scenarios. But these are kind of the vanilla extensions, let's say, or kind of the first non-trivial interactions. So the first one that I already mentioned is the kinetic mixing between the Sanan model photon, so here the field strength tensor of the Sanan model photon as we knew, and then the dark photon, which is just a massive spin like vector field, f prime mu nu. And so you just add this coupling to the Lagrangian, and then the epsilon is called the kinetic mixing. Okay, so what does this mean? Well, basically it means that if you have some electron that happens to fall into the supernovae cloud, it will experience the Lorentz force. The Lorentz force will be proportional to this epsilon, so if the epsilon is very small, then it's basically negligible, but the epsilon may not be super small. And in fact, the electric fields can be extremely large, so if these numbers don't really mean anything to you, basically what can happen is that you can boost a single electron in these electric fields up to like extremely large boost factors, like 10 to the 8 boost factors, which is extremely large. And what this means is that these particles can just pair produce. So basically what happens is that it accelerates an electron. This electron flies through the electromagnetic field of the supernovae cloud. It will send out synchrotron photons, and these photons are so high in energy that they kind of pair produce. So they produce a positron-electron pair. These get accelerated. They send out synchrotron photons again, and so on and so forth. So you produce more and more pairs, and so that you typically call this a pair production cascade, because you just need to start with a single or a couple of electrons or positrons, and you will basically produce a pair plasma through this process. So to give you a feeling of what the electromagnetic fields actually look like, so basically here is the electric field of the supernovae cloud, and it's just kind of pointing in basically one direction. And so you can imagine that if I place an electron here, it will just kind of accelerate along these field lines, and it will kind of bend around and then send out the supernova photons and produce a pair plasma. Okay, and so the end state of this pair production cascade is a turbulent pair plasma. And so here on the right hand side, I'm showing you a snapshot of basically state, this turbulent plasma state. So basically at the center you have the black hole here, and then the plane is showing you just the magnetic field strength in that plane, and then these field lines are just representative field lines that thread the plasma. And so the fact that it's turbulent is kind of shown qualitatively here because the lines are kind of squiggly. And so I don't know if you're familiar with plasma physics, then okay, this is largely magnetically dominated, but by largely I mean that in some regions it's not magnetically dominated, which means that you have efficient magnetic reconnection. What does magnetic reconnection mean? Basically it means that the field lines of the magnetic fields can kind of change their connectivity. So you have two loops and you can turn two loops into one loop. And basically this happens at these kind of reconnection sites. Now, why is this important? Well, it's basically important because at these reconnection sites you have very strong electric fields. And so at these electric fields, at these sites, you can accelerate particles. And so you inject a bunch of energy through these reconnection sites into the plasma. So basically there's a channel to convert energy that's contained in the supernovae cloud into plasma acceleration of electrons and positrons. What does this mean? Well, it basically means that you can pump a bunch of energy into the electromagnetic fields and therefore also in radiation. So like you can pump up to 10 to the 48 ergs per second into outgoing electromagnetic radiation. So 10 to the 48 ergs per second is, well, it's not the loudest, the brightest thing in the universe, but it's still quite bright in terms astrophysical sources. Now, of course, this is an upper bound, and it's a function of the kinetic mixing epsilon. So if epsilon is smaller, then this number goes down. So it's kind of the largest it can be. But from an astrophysical or just an observation point of view, these are pretty bright, and depending on where in the frequency range you are, you should be able to observe something like this.
The sources for these electromagnetic fields are charged particles?
Right, so the electromagnetic fields, they don't really have a source, because so non-zero kinetic mixing implies that the visible electromagnetic fields that electrons and positons see is no longer just the standard model photon, but it's a superposition of the standard model photon and this massive spin 1 field that makes up the super-dense cloud.
In this case, for example, in the simpler case of the scalar field, I imagine in that case that it was almost concentrated in this evil region, right? More or less.
Some amount was in the region, yeah, but the extent can be much larger than the black hole of the cloud.
And in this case,
it's basically identical. It's qualitatively identical. Well, I mean, so there's some subtle differences that the vector can sit kind of closer-ish to the black hole, but apart from that, the kind of qualitative picture is the same. Yeah. Okay, so we have found that if there's some kinetic mixing, then we can pump energy not just into gravitational waves, but also electromagnetic emissions, and the magnetic fields can be quite large. So 10 to the 8 Gauss is not quite kind of magnetar level, which is kind of the strongest magnetic fields that we have in the universe, which would be like, I don't know, 4 orders of magnitude higher perhaps. But it's still quite large, and what this implies is that that the energy gets transported into X-rays and gamma rays. Okay, so now we have some source that emits a lot of electromagnetic energy, and most of this energy most likely goes into high energy emissions, meaning X-rays and gamma rays. Okay, so you can imagine that these are signatures that we can look for not just using gravitational wave instruments, but obviously also just X-ray or gamma ray observatories. Right, and so perhaps the last thing I want to say about this, we actually did some search. So the way, there's several ways to look for this, but one way of looking for this is that you have a binary black hole merger, and then after that binary black hole merger, you expect the super-dense cloud to grow, and then eventually, if it's grown large enough, and we have some kinetic mixing, then you expect some electromagnetic signatures, meaning some X-rays or gamma rays from the same point in the sky. And basically, you can do that, or you can do something slightly different, and that is you can look through the catalog of all things that kind of pulsate at a fixed frequency. And these clouds also pulsate at we believe they have some fixed frequency that is tied to the mass of the particle. So meaning that on order 100 hertz or so, there will be some periodicity in the emissions. Okay? And so if you're familiar with pulsars, basically pulsars can have a similar frequency. So pulsars can have like hundreds of hertz frequency. And basically they emit pulses of some radio emissions every 1/100th of a second. And so it looks very similar to this. So basically what we could say is, okay, we can go through the catalog of everything that pulses at like roughly 100 hertz or so. And then we can say, okay, some of these things might not actually be pulsars, for instance, they might be super-dense clouds. Okay, and if these are super-dense clouds, then this should also emit gravitational waves. And based on these kind of analysis, you can then kind of place some amount of, well, that's not quite constrained, but you can disfavor certain masses of the dark photon. Okay, I don't want to present the results in detail, but this is just to say that we can use these electromagnetic emissions, and we can use this analysis to actually do some observations. Okay, right. I don't think this is super important, but it's just you can kind of do a similar thing now with accretion disks and access basically different masses. So here the idea is to look at EHT observations and then access supermassive black holes which correspond to dark photons that have lighter masses. But yeah, anyway, if you're interested, you can come and chat to me. But yeah. Okay, so this was the dark photons. Now, now you might ask the question, okay, now you've been talking about a massive spin 1 field. Where does this mass come from? And well, basically there's two ways of generating a mass. There's a Schickelberg mechanism, which is basically what I've been using, or just assuming implicitly so far, which is basically just you have a, you have a simple mass term in the Lagrange. Let's just leave it at that. But you might note from the standard model that all the masses in the standard model are actually generated through Higgs mechanism. Okay? So the natural way to get such a mass is through Higgs mechanism. And so this is basically written down here. So here we have GR, we have our spin 1 field, and then we have the Higgs field. So this phi is just complex scalar fields, and then with the Higgs potential here. So the Higgs potential looks like this. It's just a regular kind of Wien-Barlow type potential. Great. And then the covariant derivative is a gauge covariant derivative, which has now A in this. Okay. And so basically what happens is that as long as the amplitude of the spin 1 fields is very small, the magnitude of the scalar field sits at the vacuum expectation value V, so basically at the minimum of this potential. And what this means is that all of these kind of scalar field terms kind of break out, and the only thing that's left is kind of mass term for the spin 1 field. Okay, this is kind of the Higgs mechanism in a nutshell. Okay, so you have a spontaneously broken, or you have a broken symmetry, and that generates the mass of the spin 1 field. Great. Okay, but now of course this vector field will grow exponentially because that's the super instability. Okay, and so eventually, depending on the coupling constant, what could happen is that the vector field will perturb the scalar field away from the vacuum expectation value. Okay, it will perturb it away from the vacuum, and that will lead to dynamics of a system that differs from the super story that I've been telling you about. Okay, so basically two things can happen. The first thing is weakly nonlinear effects. Basically what happens there is that the scalar field gets perturbed away from the vacuum expectation value, and you can treat this somewhat perturbatively at higher orders, and what this means is that you can integrate on the scalar still, but the scalar now turns not just into a mass term, which would be mu squared a squared in the Lagrangian, but it turns also into an a to the 4. So basically it's a vector self-interaction, if you want. Okay? So this is kind of a weakly nonlinear effect just because it's kind of the sub-leading term to the mass term, let's say. Okay? And yeah, the long story short is that this will affect the frequency evolution of the gravitational waves. And this will be important once we go to the observations and try and understand the observational implications. Okay? This will actually be the dominant effect for most of the observations that we can do with the LDK at the moment. Okay, and then the second option is that you have strong nonlinear effects. And so basically what can happen there is that, okay, it won't just stop at the leading nonlinearity, but basically you have to just consider the full system. And there will be some new nonlinear dynamics that happens. Okay? And so basically, we at least looked at this a couple of years ago, and what he found was that, in fact, well, the name is that it's a stringy boson-nova, but basically what it means is that around the black hole, you have the sequence cloud, which is not shown in this little picture here, but you have this black hole here, and what will happen is that you will dynamically form strings. So strings are basically kind of topological defects, solutions that exist in this system of equations that describe kind of the concentration of energy along a one-dimensional line. Let me kind of, if you're not familiar with cosmic strings, they're just it's some particular solution that exists in the system of equations that basically is some kind of one-dimensional line of energy. Let me just do that. Okay. But basically, it's a highly nonlinear process that will generate the strings from a stable that is no strings. Okay. So basically, what happens is that around the black hole, you generate these strings, which then obviously disrupt the cloud completely, and most of the energy is then reabsorbed by the black hole. Okay. So you have this super instability. It grows exponentially. Eventually, you come to some threshold where these strings are formed, and then the strings could, destroy the cloud and make all of the energy collapse back into the black hole. Okay. So obviously, this will also have implications because if you're trying to place constraints on these spin 1 particles using spin measurements, you need to make sure that the black hole will actually have lost angular momentum to the cloud. And you can only make sure that that's true as long as you're looking at coupling constants or couplings that are outside of the regime where strings can be formed. Okay, so basically these are two different ways, the two kind of simplest, non-trivial ways of coupling, of moving away from the vanilla story of black hole superradiance. And it's important to look at these because of this point I've been making, that if you want to interpret observational data and you want to place constraints, you need to understand exactly when this mapping breaks down from your observation to the constraint. Okay.
That before interaction, some interaction comes as an effective QE effect, because not in the Lagrangian, right?
Right. So it's not explicitly Lagrangian, but basically you can, you can expand. You can basically expand around this solution. So where scalar field is at the VEF, and then the vector field is just a super-dense field, and you can expand around that solution to some order n expansion. And basically what that allows you to do is integrate out the scalar field from the Lagrangian. And what will happen is that once you integrate it out, in the Lagrangian you will then get first the mass term and then this a to the 4 term. Okay. Right, so I did promise to talk about spin 2 fields and why the story is a little more complicated. But so before going to the complication, I will just quickly say what I actually mean by spin 2 fields. Well, it's basically a massive tensor field, so you can, in much the same way that you write down scalar field equations and vector field equations, you can also write down the same linear equations for a massive spin 2 field. This has been known for a very long time, and so there's basically no complication there. The complication comes in when you look at basically the spectrum of solutions. Okay, so in terms of instabilities around a clear black hole, you will have a super-dense instability, which we already discussed, and it's basically happening in much the same qualitative way. But then additionally, you have a monopolar instability, and you might recall from the lectures that you can have a super-dense instability only for n not equal to 0 modes, right? And these are the modes that carry angular momentum, and so the super instability extracts angular momentum from the black hole, so you have to convert that energy into a state that carries angular momentum. Okay. Now the m equals 0 mode doesn't carry angular momentum, so this is just not unstable to the super instability. But as it turns out, for spin 2 fields, there is a monopolar instability. Okay, and so this has some origin in like high-dimensional gravity, like if you know the Gravitational instability, it's basically identical to that. There's some mapping there, but if you're not familiar, it's not too important. The bottom line is that there's some monopolar instability. And so basically, here you can see the growth rate, so that's the imaginary part of the frequency that I introduced during the lectures. You can see the growth rate as a function of this combination of the mass of the spin 2 field and the mass of the black hole. Okay? And so what you can see, basically they're classified by their azimuthal states, so m equals 1, m equals 2, m equals 3, as well as m equals 0. And so m equals 0 corresponds to these solid lines here, with the circular dots. Okay? And basically what you can tell from this plot, and there's lots going on, but the important takeaway from this plot is that the solid lines are all above the dashed lines and the dotted lines. Okay? And what this means is that this monopolar instability, meaning the m equals 0 instability, has growth rates, or imaginary parts, that are larger, potentially also magnitude larger than the super-dense instability. Okay? So dynamically, the relevant feature here is not the super-dense instability, but instead the monopolar instability. Okay? And so this monopolar instability has much different qualitative features, both in the linear regime as well as the nonlinear regime. And so basically you can't just translate the super-dense story from the spin 0 and spin 1 up to the spin 2 field and expect it to hold much the same way. Okay? Okay, but now you might be suspicious because now we're talking about the monopolar instability, and so this might actually be present in non-spinning black holes. And that's exactly true. So massive spin 2 fields are unstable on the Schwarzschild background. And so that can already lead to very peculiar behavior. And so let me outline the peculiar behavior in one slide. Basically, yeah, so it's, you have this instability in a Schwarzschild background. It is the most relevant, meaning that the growth rates are the fastest because, well, in Schwarzschild there's no superimposed instability, so it's the only instability. And lastly, it extracts energy. And this, again, you should get suspicious because now you have a non-spinning black hole and you're extracting energy from a non-spinning black hole. But as I told you, the irreducible mass of the non-spinning black hole is irreducible because you can't increase the area of the black hole. You can't decrease the area of the black hole. But you can only decrease the area, you can only not decrease the area of the black hole if the matter that you throw in satisfies an energy condition. Okay, so spin 2 fields do not. And so they can actually extract energy from the black hole without breaking the area theorem. Okay? So the black hole actually shrinks as it kind of absorbs this massive spin 2 fields. And so what you now need to picture is the following. You have some black hole with some mass, no spin, and then you have a way to extract energy from this black hole. Okay? And it's an unstable process. So basically what will happen is it's not self-regulated much in the same way that superimposed instability is regulated. But basically you're just extracting more and more energy, and so that the black hole shrinks more and more and more over time. Okay? And so in the linear regime this cannot be stopped. And so the question is, in the nonlinear regime, what happens? Is there a process that kind of regulates this instability and stops the black hole from shrinking to 0 size, basically? And so what we did is analyze this in a toy model. Toy model. It's basically Einstein-Wire gravity, which is it's basically the Einstein-Hilbert action plus the square of the Riemann tensor. Well, it's the square of the wire tensor. But basically, what it means is that you propagate a massive and a massless spin 2 fields, and you can ask the question: okay, what happens in this nonlinear theory where you can couple this massive spin 2 field to gravity? What happens in the nonlinear regime of this instability? And basically, the bottom line is that these nonlinearities, at least for this particular theory, cannot stop this collapse to like 0 size. Okay, so this part is showing you basically, it's basically showing you 1 over the mass. The solid black line shows 1 over the mass. And so, if the black hole mass goes to 0, then this will blow up in some finite time. And so the x-ray is just time, and so what you can see is basically, yeah, exactly this happens. The black hole's mass goes to 0, and at the same time, curvature invariants blow up. Okay? So basically, in this particular theory, and this is of course theory specific, so a different way of coupling massive and massless spin 2 fields might give a different result, but in this particular theory, what you find is that this instability will just create a black hole of 0 mass, as far as we can tell. Okay? I should caveat this because, well, these are all numerical simulations and we never go to zero mass and 0 size, so there's room for things kind of happening at a very, very small scale, but it would be somewhat surprising if that were happening. So basically this is just to say that, okay, the spin 2 field behaves very, very differently from like the spin 2 and spin 1 story I've been painting. And there's lots of things that need to be worked out before we can even think about connecting those two observations.
The actual, if you add a logarithmic x scale, it would help to see what is the power of time which it explodes. This way it's hard to tell. But would that be meaningful to get the power of time? If it's a 1 over t, 1 over t cubed? Meaningful to some extent to know that?
I'm not sure it would be telling you much. Well, it would be telling you something, but I guess I wouldn't quite know what the physical implications of that would be.
The fundamental level.
In fact, if you just use linear theory and you kind of assume that the solution will go through a sequence of Schwarzschild black holes with smaller and smaller mass, you will find exactly that it goes linear in time, or 1 over 1 over time. And that seems to align well with the nonlinear simulations too.
No, you can tell in this any curve collapse to infinity there.
Yeah, perhaps. Okay. So, right, let me skip that. Okay, so now observation. So I've been telling you, a lot about theory, and that we need to understand not just the vanilla story, but also what happens if you couple it through the obvious ways to the standard model. And this is all just to actually be able to interpret observations. Okay. So how can we connect the theory I've been telling you about to observations? And so basically, search techniques for the presence of these superdense clouds kind of fall into, well, 4 different camps. Maybe there's more, but these were the ones that I kind of looked at. So the first, perhaps obvious one is, okay, let's make black hole spin measurements. Okay, so as I said, if you can find some population of black holes with spuriously small spins, you might infer the existence of these clouds and therefore the particles. We are notoriously bad at measuring black hole spins, both with electromagnetic observations and also gravitational wave observations. And so basically spin measurements at the moment are just not at the accuracy level that you need them to place confidence constraints. Okay. Second thing that people have been doing is like all-sky continuous wave searches. So by continuous wave searches, I mean people look through the LIGO data and they're looking for a gravitational wave that has like basically a fixed frequency and a fixed amplitude, and they try to look for these kinds of gravitational waves. Okay, and they do this in various different ways. And one way they're doing this is through an all-sky search, meaning they're just agnostic to where the signal is coming from, but they just look over the entire sky and try and find ways, these continuous gravitational waves. And so these constraints are not super sensitive because obviously if you look for the entire sky, it's computationally quite expensive. So the constraints aren't super, the upper bounds on the gravitational wave amplitude aren't the most sensitive. But it also means that even if you have very sensitive upper bounds on the gravitational wave amplitude, translating that into constraints on these spin 0 fields would be tricky because you would need to understand the population of black holes that actually generates these gravitational waves. And well, basically the bottom line is we don't have a good understanding of black hole populations in the galaxy, and we have detected like let's say 100 binary black hole mergers, so we still have kind of starting points of understanding black hole populations. So there's this problematic assumptions that you need to make, and then of course loss of sensitivity because all-sky searches are very sensitive. Okay, so the next step would be, the step up from the all-sky search would be a targeted search. So here you're looking at a specific black hole that you know exists. So like, in the galaxy we know of specific black holes through electromagnetic observations. We have some, mass measurement and potentially some spin measurement, although those are kind of shaky. But nonetheless, we can target these systems with continuous wave searches. And so then the assumption is that these black holes exist and they have some cloud that still remains after the black holes have existed for many, many years, potentially many years, we don't actually know the age, but the assumption is that at the present time they still have a superdense cloud that still emits gravitational waves. And so you can look for these gravitational continuous wave searches and you can kind of go deeper into the data because now we're looking at just a single point source on the sky, basically. Okay? That way you can increase sensitivity. The problem here is that you still need to make assumptions about the black hole properties. Okay, you have usually a pretty strong measurement of the mass. But again, we don't know the age of the black hole, meaning we don't know if the cloud is supposed to still be there and still emitting, or has it already, kind of emitted all of its energy into gravitational waves. So we don't know the age, and we also don't know the spin, typically. And so the spin is kind of very relevant because the superdense process only happens around spinning black holes. Okay? So while we are very good at doing these targeted searches, we still need to, in order to translate this into actual constraints, we still need to make assumptions about black hole properties that we can't actually directly measure. Okay? And so kind of the last point is the best way, or the quote-unquote best way of doing this that we have come up with so far, which is follow-up searches. So here the idea is that you have a binary black hole merger, and then you have a new black hole with some measured mass. So we know the mass pretty precisely. It has some measured spin. We know the spin relatively precisely, and usually the spin is like 0.7 or something. So the spin is relatively large. And so now we can just follow up this binary black hole merger with more continuous wave searches. Okay? And the idea here is really that we make the least assumptions, because we know exactly the age of the black hole. We know exactly the mass and the spin of the black hole. So basically there's 0 assumptions we need to make. And so with that, you can place the strongest constraints because you can also now do a very deep search for the continuous waves sent out in systems. And so, to estimate exactly how sensitive we are to these types of searches, we kind of adapted the continuous wave search techniques that have been developed for other sources in the LDK and used them for these follow-up searches. So this is specifically for vector fields. For scalar fields, it doesn't work as well because the luminosities aren't as large. But let me just focus on vector fields here. So basically, what I'm showing here in this plot is on the x-axis just the initial mass, so it's the mass of the remnant of the binary, and on the y-axis the spin of the remnant of the binary. Okay, so here they're called initial, but really in terms of merger they're the final products. And then in color, I'm showing you here the horizon distance out to which we can observe the continuous waves that are sent out from the same super-dense cloud after merger, basically. Okay, and so the bottom line is that up to, well, if we're generous, up to 6 gigaparsecs, so like order gigaparsec, you can potentially observe the continuous waves from these types of systems. And obviously, if the spin is low, then you lose sensitivity. And then also, if the mass is very light, you lose sensitivity. And of course, if the mass is too large, you also lose sensitivity.
That's for the dark photon.
Yes. And so this little corner in the top left is basically here the coherence time, which is basically a way to chunk up the data for these continuous waves algorithms. The coherence time becomes too small, and the reason for this is the frequency of the continuous wave evolves in time. And the evolution in time can be too fast for the algorithms to keep track of. And so basically, in these systems, which are highly spinning and very light, just the frequency evolution is too fast for these methods. And so, yeah, we just can't use the methods in those regimes. Now, unfortunately, this is kind of the interesting regimes because it's large spins and light masses, but okay, this is just a limitation of the method. Yeah, and so these white lines just indicate, okay, these are the type of masses you could, roughly speaking, constrain with observations that fall into this regime. Okay?
Largo goes pretty well, no? Because you are at the range of few hundred megaparsec.
Yeah, for sure. So based on this plot, you might say, okay, it's there are events that fall into this horizon distance. The problem with actually doing this in the data, well, there's just several things that are confounding. So, like for instance, one would be, for CPC for a magnetic black hole merger. You need let's say a second of data to observe and characterize the system. For continuous waves, you need weeks and months of continuous data. And if the data is gone in a week in between, you're using all the SNR that was in that gap. Okay? And so there's just unfortunate events that are we should be sensitive to here, but just the day after that event happened, the detector was off for a week or something like this. Okay, so there's practical limitations that cause these types of things. And so, yeah, so what I can say is at least for O3 and all the preceding runs, none of the events are actually super exciting in terms of conducting a real search like this. Basically because of these practical limitations. But yeah, it's just a matter of time to get lucky, basically.
Is there a push within the continuous wave group to extend the data?
Yeah, well, there was some communication to the people that keep the detector online. As far as I can tell, is that the bottom line is that it's really hard, and I'm not sure that this request actually went all the way through. But yeah. Okay, so this is for ground-based detectors, and here the bottom line is okay, we're kind of sensitive, but also not really because of these practical problems. But this is restricting to 03 and before, and so maybe 04 or 05 things will be different. And so now going to space, well, maybe the last thing I should say about this is that we did the exact same analysis for the Einstein telescope and the Cosmic Explorer, and well, the answer is kind of it's identical more or less, and you just gain an order of magnitude horizon distance. which roughly makes sense. Okay. And then for LISA, we kind of, well, we did somewhat similar analysis. So here, the idea is exactly as before. You have some supermassive light in a black hole that merges, produces a new black hole with some given mass and spin. And so here on the x-axis, I'm showing the mass of the, well, this is just for some fiducial numbers, but I'm showing the mass of the remnant black hole. So it's like 10 to the 5, 10 to the 6-ish solar masses. And then luminosity distance on the y-axis in megaparsec, and then the redshift just for reference. And then these numbers here just correspond to the SNR, so the signal to noise ratio, with which we would be able to detect these signals from these types of systems. So basically, the bottom line here is that if you know, let's focus on this one. So that's 2, 3, 4, 5 times 10 to the 5 solar mass black hole. And if that merger happened, you know, at 2 times 10 to the 2 megaparsec, so like 200 megaparsec, which would be extremely close, so probably not. But if that happened, then the SNR would be 20,000. So we could very, very confidently look for the signal, and if we didn't see anything, we could rule out much of the parameter space, basically. Obviously, for supermassive black holes, you know, it's not going to be at 200 megaparsec. But you know, we don't really know what the population of supermassive black holes really is. That's kind of an open question. But certainly, in the regime of up to like order a few redshifts, there will be supermassive black hole binaries. And so if they emerge, we can kind of conduct a similar search with LISA data and then place constraints in much the same way. But of course, now we wouldn't be placing constraints on dark photons of mass 10 to the minus 13, 10 to the minus 14 electron volt, but instead 10 to the minus 15, 16, 17 electron volts. Okay, so these two are complementary in the sense that they cover different regions of the dark photon parameter space. Yeah, and I should say that, okay, all of this is for vectors, and for vectors the follow-up searches are kind of more favorable. But you can do look for the scalar in slightly different ways, similar to what I listed before, and access those as well. Okay, and so, right, so this is all assuming that you just have the vanilla superaliens. But I've kind of made a point that, okay, you need to understand other coupling as well to be able to, map those into these two-dimensional plots that particle physicists want to see. And so basically, then the question is, okay, how is the gravitational wave signal that you're detecting and using to constrain these particles, how is this modified due to these additional couplings? And basically, the modification falls into two kind of obvious camps. The amplitude is modified or the frequency is modified. And so for continuous wave searches, the most problematic thing is that the frequency evolves more quickly. And so you just lose track of the signal if it evolves too quickly. Okay? So the amplitude is not all that important, actually. And so now if you understand basically the impact on the frequency evolution of these gravitational waves, is a function of the new couplings, so here the kinetic mixing, or in the Higgs case, the Higgs couplings. If you understand those, then you can map the constraints that you can place on just the vanilla, spin 1 or spin 2 fields, into constraints of the dark photon, meaning a spin 1 field that is coupled to the dark photon through the kinetic mixing. And so basically, the bottom line is that we went through this exercise and did this explicitly for these types of follow-up searches. And basically, what you get is a plot like this. So here, just like on the first slide, on the y-axis you have the kinetic mixing of the dark photon, and on the x-axis you have the mass of the dark photon. And then in the, this is brownish and bluish, those are the existing constraints from some other observations that were made in the past. And so all this white space down here and all the way down to zero kinetic mixing is basically not constrained at all at the moment. And so basically this shaded area here corresponds to the region of the parameter space that you can access with these follow-up searches of binary black holes. And basically constraints you get from these follow-up searches can be mapped to precisely those regions of the parameter space. So you can basically rule out everything from epsilon equals 0 all the way up to basically the regime where we've already ruled out everything. Okay, so this kind of makes the point that microsuperance is a very powerful probe to look for these particles, because basically you can rule out the entire existing remaining parameter space that people haven't actually ruled out yet. Okay, so that's pretty good. And then yeah, okay, so you can do the exact same thing for the hexabillion model. The couplings are a bit less meaningful perhaps, but yeah, the story is identical. You just need to understand exactly how the frequency evolution changes with the coupling parameters, and then you can place constraints. Okay, so just brief summary is basically, okay, waveform modeling, basically super and story, if you just consider gravitational interactions, is pretty well understood, and so there's a question just of, okay, we need to get more data, and eventually we'll be able to place constraints. But there is value in understanding non-gravitational interactions because of these plots that I just showed you, that you don't just want to place constraints on basically the mass of these particles, but you want to understand, okay, how does this relate to the QCD axion self-interactions, for instance, or the kinetic axion, okay? To put this into relation and connect it to existing or other observations and constraints. Right, and then there's, you can do certain things that, have kind of not been worked out so far, but let me just leave it at that. Questions?
Do you model at the moment
So super rad includes m equals 1 and m equals 2. It does not include, well, it includes the known analytic stuff for higher order than m equals 1 and m equals 2, which is usually not super accurate. So.
I guess presumably they're important for this.
Potentially, I guess. The thing is with higher order modes that the gravitational wave amplitude decays exponentially with m, basically. And so very quickly you run into a regime where you just can't observe it anymore. But yeah, it's possible and perhaps plausible that the first few higher order modes will be relevant for observations.
If you go to supermassive black holes, so the Schwarzschild values increases, so you're probing smaller masses of your whatever dark photon or scalar. And but did you analyze the phenomenology of these systems? Superradiance of clouds and supermassive black holes?
Yeah, basically the phenomenology is identical. The only difference is that the numbers change. Like for instance, in this plot, yeah, you can play the exact same game with different masses, and then Lisa, and yeah, basically you can figure out the horizon distance much the same way. Of course.
But it goes to 0, no? And the scale, the end scale of the x-axis is 10 to the 6.
Yeah, something like that.
So if you go to 10 to the 7, 10 to the 8, why is it negligible? What happens?
So here we pick this fiducial number because basically, so with Lisa, so this was specific for Lisa. And Lisa is meant to observe only for like order 4 years or maybe a bit more. But you need, because the masses are so much higher, so the time scale also scale with the mass basically. And so you need to collect enough SNR over the mission duration.
Mm-hmm.
And if the black hole's mass is too large, then all the SNR happens outside of your observing orbit.
Okay. The rate goes down basically.
Yeah, you just lose sensitivity basically.
Okay. So AGNs are not interesting.
Yeah, well, yeah, if they're heavier than 10 to the 7, then they're probably not.
Yeah, I mean, the bulk of the engine of the AGN are massive.
Yeah, but you can access those regions by doing like the dark. So I didn't mention this explicitly, but I mentioned it in passing. So here, this is a busy plot. It's not important what's actually going on, but basically what we're looking at here is to use EHT observations. EHT observations. Event Horizon Telescope. And there, if you look at M87, it's like roughly 10 to the something like a few times 10 to the 9 solar masses. And so that's a completely different part of the parameter space, which you can then use electromagnetic observations instead of gravitational observations.
Yeah, but then you just said on the scale, the time scale of the emission is longer. No, it's longer than the year scale. I mean, whatever we can do is year scale. I mean, 10 years. But, I mean,
Right. Right. But for the EHD, you're not looking for you're not looking to collect SNR or something. You're looking for other signatures that are on shorter time scales, let's say. For instance, the oscillation frequency of the cloud is.
yeah, but how would you see it?
Well, you will see it through. So one way you can see it with the EHD would be through polarization signatures that vary on the time scale of the frequency of the superdense cloud. And of course, you have to be careful about disentangling this from astrophysical sources of periodicity. There's certainly big caveats there, but that would be one way of doing it. And these time scales are much shorter than the gravitational wave emission time.
Yeah, but you don't have fundamental model for the coupling of the boson cloud to, say, the plasma. You just assume heuristically that the boson cloud will even increase the same.
No. You can derive this from first principles. You can impose this. You can put this in the Lagrangian, and from there everything follows.
Okay.
I mean, well, you know, I say everything follows. You need to make assumptions like, you know, the typical plasma assumptions like, okay, you can derive it, you can describe it as GMHD, and these kinds of things. But then once you go to that level of GMHD, which is the level of all of astrophysics basically, you can basically derive exactly what the impact of this would be onto magnetized fluid, and then you can do the exact same analysis. Which is basically shown here. I didn't actually explain what's going on.
So why did that photon, I mean, is more sexy than the boson, or just another case?
Right, so why the dark photon compared to the scalar, I guess. So the scalar, well, the scalar is actually more interesting from a high energy motivation point of view, like particularly QCD axion, because it solves the strong CP problem. So the scalar is actually perhaps in some sense more interesting from a theory point of view. From an observational point of view, it's just much harder to make observations because the timescales are shorter, the luminosities are lower. And in particular, if you couple it to other things, it becomes a lot more tricky. So for instance, the axial photon coupling that I mentioned, it will in principle have some impact on like recruiting systems like these. But to make that more explicit is just tricky for technical reasons. I could go into more detail, but basically it's just harder to figure out. And so the question is not the dark photon is more sexy, it's just that it's easier to deal with. And it's still well motivated, so it's not just some crazy idea. And so, yeah, so in particular, when it comes to the coupling to the standard model, because you can couple the photon and the dark photon in a different way than you couple the axion to the photon. The physics is just much different. Generally, the expectation is that the decaying mixing induces more observable signatures that are easier to see than axion photon coupling, at least in the context of superradiance. But I mean, people look for these things with like pulsars, for instance. So like or magnetars. So like you can convert photons to axions in pulsar magnetospheres that people do, for instance. So people do astrophysical searches for axions.
So now fast radio bursts are hot.
Right, yeah, they are like, I mean, we don't even understand it from an astrophysical point of view, so.
Yeah, so one is more to propose.
I'm sure people have done that. I'm sure people have written about 5 different models for experimental axions. But the prior should always be it's not new physics.
This axion field, I don't know the details, but when you speak about the strong CP problem in the QCD context, what confuses me is this scalar field that is spread about all space-time, and the existence of this axion field could resolve some problem with QCD.
Yeah, so the answer to your last question is yes. That's by construction, basically. So it was invented, quote unquote, to actually solve the strong CP problem. So the QCD axiom was engineered to give an explanation for why a specific term is zero in the Lagrangian that you wouldn't naturally assume is zero. Okay, so in that sense, yeah, it solves the strong CP problem by design. Okay, there's this, somewhat of subtlety that people call axions all sorts of different things. So then needs to be the distinction between axion-like particles and QCD axion, which are two different types of things, but they're both scalar particles. So there's some subtlety there, but quote unquote the axion, the QCD axion solves the strong CP problem by design.
But for example, if there's evidence for these scalar particles, there are candidates to solve the strong CP?
It depends on the mass. Yeah. So the strong CP problem is basically there's an expectation of what kind of mass range it should sit in, the QCD axion. And so basically this mass range goes from like, I don't know, rough numbers are like 10 to the minus 12 electron volts to higher masses, basically. And so if you find a scalar particle that's below that, it cannot solve the strong CP problem. So there's kind of a distinction between QCD axion and other axions, let's say. But of course, any particle you'll find will give you hints on high energy physics, basically. And it's just that the QCD axion is perhaps the best motivated because we have a theory that describes particle physics extremely well, yet somehow there's a problem.
Visit of Nils and Max, but they will be here tomorrow. Yes. So let's thank Nils again. I need to go. We can have a final dinner. So.
Oh, okay.